add. All right, 5, 4, 3, 2. Good luck, everyone.
Good morning. People are still rolling in, and so we'll get this webinar started shortly. We'll just give it another 30 seconds to a minute. Okay, why don't we get started? People are still rolling in, and but we do want to end on time today. So welcome to today's webinar for the second in our series for the Future Supply Actions Funding Program. My name is Warren Teitz. I'm a team manager within Metropolitan's Water Resource Management Group, and also the program manager for the Future Supply Actions Funding Program. I'll also be your moderator for today's webinar. This webinar will be recorded, so please keep your microphones off. You may hear my dogs. I apologize in advance, but that's just the way it goes sometimes. The recording and the slides will be available on our website relatively soon. We plan to have time for questions at the end of the presentation. Please type your questions in the Q&A box, and we'll get to them again at the end of the presentation. We value your time. This webinar is scheduled for about 45 minutes. Most of it will be for the presentation, and we hope to end on time. Next slide, please. Next slide. Okay, so just a quick introduction to Metropolitan. We're the nation's largest wholesaler of imported water supplies. We serve about 19 million people, a $1 trillion economy, 5,000 square mile service area. We sell water to 26 member agencies who then in turn sell it to retail customers, or some of them are wholesalers in their own right. And we import water from the Colorado River and the State Water Project, but that's really only one facet of what we do. So next slide, please. The slides are, there's a little delay. So for the past 30 years, we've been diversifying our resource portfolio through investments in conservation, local resources, and storage and exchanges. And we've invested about $1.5 billion in these local supplies. It's part of our One Water approach to building climate resiliency into our reliability in our portfolio. And innovation is a key part of that. That's really the goal of this Future Supply Action Funding Program, is to sort of drive innovation with local supplies in partnership with our member agencies. Next slide, please. So we initiated the Future Supply Action Funding Program in our 2010 IRP with the goal of wanting to be able to accelerate these local supplies if we needed them in the future, not just for climate change uncertainty, but for all kinds of uncertainty that our region faces. We wanted to drive innovation and pilot new approaches, and piloting and these demonstration studies de-risk new technologies so that we can safely integrate them into our practices. We want to do that by removing technical, institutional, and regulatory barriers. This particular study addresses regulatory and technical barriers to surface water augmentation, potable reuse. And finally, each one of these studies benefits a particular member agency, but they were selected on the basis that they benefit the region. So we want to share this information with other water agencies that can benefit from the lessons learned from these studies, and then as they develop similar projects. The 4 resources covered by the FSA include groundwater, stormwater, potable reuse, and desalination. Next slide, please. Our current program includes 14 studies that we've partnered with our member agencies, and we're co-funding about $3 million from Metropolitan funds, but I think it's close to $7 or $8 million that our member agencies are investing. So we're leveraging a lot of money with regionally with this program. We also have invested about just under $1 million with the Water Research Foundation for 6 potable reuse and 1 agricultural reuse study under the FSA program. So next slide. At this point, I'd like to turn it over to our member agency partner, Jeremy Crutchfield, to say a few words and to introduce our speakers for today. And I'll see you at the end of the webinar for the Q&A. Thank you. Go ahead, Jeremy.
All right, thanks, Warren. And again, my name is Jeremy Crutchfield. I'm a Water Resources Manager for the San Diego County Water Authority. Before I introduce today's speakers, I want to thank Metropolitan for partnering with the Water Authority and Padre Dam through the Future Supply Actions Funding Program. The demonstration project being presented today supports the East County Advanced Water Purification Project, which is a key part of the San Diego region's effort to further diversify its water supply. Just want to say it's been great coordinating with Warren and our agreement administrator, Don Bailey, throughout this project. It's been a real fascinating project to be a part of and engage in. But with that, it's my pleasure to introduce our 2 speakers today. I certainly don't want to steal any of their thunder getting into the details. So with that, Saval Sen will lead off. She's an engineering manager at Padre Dam Municipal Water District. She'll be followed by Luciana Pereira, who is a PhD and engineer with Trussell Technologies. So with that, Saval, it's all yours.
Yes, thank you, Jeremy. And good morning, everyone. So I wanted to start us with giving you a little bit more background on the our project that we are currently working. It's the East County Advanced Water Purification Project. Next slide. So this project is a joint effort among 4 participating agencies. These are Padre Dam Municipal Water District, County of San Diego, Helix Water District, and City of El Cajon. So just recently, this is a very young Joint Powers Authority, but East County AWP Joint Water Authority was formed last year in November in an effort to administer this project and also finance this project. So the wastewater agencies formed the JPA, and their role will be to have wastewater services agreements with the wastewater collecting agencies, and also have this project treat the wastewater, turn that into a raw water supply, and sell those water supplies to Padre Dam and Helix through the water purchase agreement. So this system was set up, and we've been working tirelessly for the last year to push forward with this project. Next slide. So a little bit of our goals of the project. Why are we doing this? It's really to create a new local, sustainable, drought-proof drinking water supply in our community. And the project size is about 15 million gallons a day, gallons a day of wastewater, eliminating that discharge into Pacific Ocean and capturing it where it's generated and turning that into a local water supply. And it will create up to 30% of our drinking water demand in our region, in our customers' demand. And it will, in return, reduce dependence on the imported water. Next slide. Getting into a little bit of more detail. So this is our area. This is in East County, East San Diego County. So there's about 15 MGD of wastewater projected to kind of generated by the online time of this project. And currently we generate about 14 MGD. So we are not far off of that. But currently we only take 2 MGD of that wastewater and send it to the Ray Stoyer Water Recycling Facility owned and operated by Padre Dam, and turned 100% of it to recycled water use, and also supplement and feed the Santee Lakes Recreational Preserve. But the remaining flow, it's discharged to the City of San Diego's collection system and send it to Pacific Ocean through Point Loma wastewater treatment plant. Next slide. So with the implementation of our project, what we are proposing, we are not going to waste that wastewater and capture all of it from all the partnering agencies and direct it to the new wastewater, expanded wastewater treatment plant that we are currently working on. And it's not only the wastewater treatment plant, but we will also couple it with the advanced water purification facility to produce raw water that's suitable for discharge into Lake Jennings, the local reservoir, as you can see on this figure. And Lake Jennings is owned and operated by Helix Water District, another partner of the project. And this water will be once again treated at their water treatment plant, levee water treatment plant, before it's served to the customers. So that will generate, 30% of our demand, as I said, between Helix Water District and Padre Municipal Water District service areas. Next slide. A little bit about the implementation schedule, just to set the stage. So we this is such a huge project for us. So we broke that into 3 packages, more manageable packages, and to address the skill sets for the contractors. So package 1 is everything about treatment. It's the wastewater treatment plant. We will have a solids handling facility with digesters and the advanced water purification facility. Package 2 is the product water pipeline, 11-mile pipeline, taking that product water from wastewater treatment plant to the Lake Jennings, and wastewater conveyance, all the improvements, it's repackaged under package 3. And they're being done by different design builders on board. We are executing this project using a progressive design build method. So we are in the midst of design. We are going through 60% design right now, and we plan to be online by mid 2025. And I wanted to also mention like the AWP demonstration facility that we've been operating since early 2015. This facility served us very well. We've been running it for 6 years now, and it just recently being retired. But that served very great purposes, as I highlighted on the right here. So we used this to get regulatory approvals at the time when the project was just a Padre Dam little project. So we were looking for a groundwater recharge. That's why you see that it says minimum aquifer storage. That was one of the purpose, but we moved away from that since then. But we used the facility. It allowed us to pilot test different technologies, different things. And this is where we pilot tested this study as well. And yeah, we also then gained some operator experience on a membrane facility that we never operated before. So Padre Dam operators were taking care of the operation and cleaning everything for this demonstration facility for 6 years. So that was a great benefit. And also we used heavily on the public outreach. Hopefully some of you guys came to the site and visited our demo facility and got one of our tours. So just wanted to mention that and give a visual, because this is where we tested this study. I believe that's my last slide. So I will turn this to Luciana to get us more details about the study that we've done.
Thank you, Seval. Hello, everyone. Just want to make sure that everyone can hear me. I'll take that as a yes. Thanks, Warren and Jeremy, for the introduction too. So I'm going to tell you more about this study, and I want to start by giving you some of the regulatory context and the motivation for this study, and that has to do with the California Toxics Rule, or CTR. This is a regulation that establishes water quality standards for inland surface waters like Lake Jennings and other bodies of water, with the objective to protect aquatic ecosystems and human health. So the CTR regulation will apply to the discharge of purified water to Lake Jennings, and that's why we are interested in it. So in this study, we looked at a subset of the CTR constituents. CTR establishes limit for about 126 chemicals, and we looked specifically at disinfection byproducts, or DBPs, which are formed by compounds that are in the source water when they react with chlorine. And in particular, we looked at a specific group of DBPs, which are trihalomethanes, or THMs. So here in this table on the left, you can see the 4 THMs that are regulated under CTR. So there are 3 brominated ones: bromodichloromethane, or BDCM, dibromochloromethane, or DBCM, bromoform, and chloroform. And under CTR, each of them has its own limit. And the CTR limits for BDCM and DBCM are pretty strict, 0.56 and 0.41 micrograms per liter. The 4 THMs also have a maximum contaminant level for drinking water, or MCL. And this limit is for the sum of the 4 of them, and it's at 80 micrograms per liter. So it's higher than the CTR limits. So this is the demonstration facility that Seval introduced in her presentation. And as she mentioned, we did a lot of studies with this pilot plant, and we did one year-long study between 2015 and 2016. It was a demonstration study where, among other things, we monitor the water quality along the treatment. And that is what I want to show you on this slide. On the figure on the left is the concentrations of BDCM in green and DBCM in red along the treatment. And the treatment processes that we're looking at are at the bottom of the figure. So the secondary effluent is the feed water to the pilot treatment. And the concentrations of these 2 THMs were below 0.5 micrograms per liter. So they were not detected. And you can see the CTR threshold in dashed lines. Now, the first treatment when the water comes in is to add chlorine and allow some contact time for disinfection, and then ammonia to form chloramines. And what we saw in the effluent of the free chlorine disinfection treatment was that the concentrations of the 2 THMs increased. So we were forming them. And then as the treatment continues, we do reverse osmosis and ultraviolet advanced oxidation. So the concentration decreased, meaning they are partially removed. But in the product water, you can see here in the UV AOP effluent results, the concentrations of the 2 THMs were above the CTR limits, particularly for BDCM. So these observations prompted a study, a desktop evaluation of different options to see which one we could use to achieve CTR compliance for these 2 THMs. So these are the 3 options that we looked at. And the first one is the establishment of a mixing zone. So this would be a zone within Lake Jennings, within the reservoir, where the project would receive credit for dilution or for constituent decay, and the CTR limits have to be met within the boundaries of this zone, as opposed to being met in the pipeline right before discharge. So this is an appealing option because it has no capital or infrastructure investment. But there are several studies that were required for the regulators to consider this option, and it was just not compatible with the timeline of the project, so we didn't select this option. Another option is the one in the middle, which is air stripping, and this option means that we will separate the THMs because they are volatile, so we can use air stripping towers to do this. This is a proven engineering technology, but it has higher capital and operational costs. so we did not select it. The option that we selected is the one on the right, which is the use of preformed chloramines. And I will tell you more about this because that's the topic of this presentation. But we selected it because it's a cost-effective option and is proactive, meaning that instead of forming these THMs and then finding a technology to remove them, we are implementing a strategy that minimizes or prevents their formation altogether. So I will tell you more about the preformed chloramines. What we're looking at here is the treatment, the advanced treatment for the full-scale project. So if we start from the left, and I think, yeah, you can see my pointer. So if we start from the left, we're going to be treating tertiary treated wastewater, and it's going to be treated by membrane filtration, reverse osmosis, ultraviolet advanced oxidation process, or UVAOP. And then this product water is going to be transported to Lake Jennings. And during that transport, we're going to do a free chlorine disinfection. So if you look at this treatment train, you can see that at different points in the treatment, we add chlorine or HOCl. So if we start at the end of the treatment, we use it for disinfection. In UVAOP, we use it as an oxidant. And here at the front of the treatment, we add it together with ammonia, and that is to form chloramines. And chloramination of the feedwater is a common practice when we have membrane processes, because the goal is to prevent biological growth and biofouling of the membrane processes. So we could do this, for example, with free chlorine. We're going to prevent biological growth, but free chlorine is a very strong oxidant, so it's going to damage the membranes. So instead of doing that, we form chloramines that are mild oxidants, so they are not as damaging to the membranes, and they can still prevent biological growth. So this type this form of addition of chlorine and ammonia directly into the feed water is what we call inline chloramination or conventional chloramination, and that's what we did during the demonstration study. So if we could zoom in this part of the process and see what happens with the chemistry, we would see something like this figure in the bottom left. So we have the tertiary treated effluent coming in, and this has some organic and inorganic constituents, and some of them are DVP precursors. So for example, inorganic DVP precursors are bromide, that is involved in the formation of all the brominated THMs and also bromamines. So what happens when we add chlorine, which is a strong oxidant to this water, is that reactions are going to take place and DVPs will be formed. For example, the 4 THMs that I mentioned before. We're also adding ammonia to form the chloramines. So we effectively form the chloramines, but with the ammonia now we can form bromamines too, and those could damage the membranes. And once we have chloramines in the water, there are reactions that can take place with chloramines too, and the constituents in the source water, and that could lead to the formation, for example, of NDMA. And NDMA is another chemical that's regulated under CTR. It's a CTR constituent, and it also has a notification level for drinking water. So the idea of using preformed chloramines is that we will prevent these reactions from happening. And the way to do that is with a simple change in the process, which is shown in this figure on the right. So instead of adding chlorine and ammonia directly to the feed water, which is this thick arrow, we added to a side stream of water that's very clean. It has very low content of organics and inorganics. So when we mix them, we only form the chloramines and avoid all these other undesired reactions. And one type of clean or clear water that we can use is aeropermeate. So this has low capital and O&M costs. There is some additional equipment that's required compared to inline chloramination, but it's minimal. These are some examples of the use of preformed chloramines in full and pilot scale projects. The inline chloramination or conventional chloramination is the common practice in drinking water and also in groundwater recharge. But the use of preformed chloramines is gaining traction here in the US and for potable reuse. So we have some examples at pilot scale. For example, the West Basin desalination demonstration. that used preformed chloramines to reduce bromamine formation. DC Tillman looked at preformed chloramines to control NDMA formation. And the Pure Water San Diego Phase 1 project, which is another surface water augmentation project in the region, is looking at preformed chloramines to control bromamines. And at full scale, there's a plant in Perth, Australia, that uses preformed chloramines for DVP control, and also the new water facilities in Singapore. So going back to our demonstration facility and our own study, we installed a preformed chloramine system at the demonstration facility and monitored the performance and the water quality for 12 months. And this was to see if using this strategy of preformed chloramines could help us achieve levels of THMs in the product water that were compliant with the CTR requirements. This is the test plant that we developed. The treatment train that you see here is what we're using at the demonstration facility. So we have secondary effluent coming in, and it's treated with membrane filtration, reverse osmosis, and UV AOP. And we sample along the treatment in the feed, in the RO feed, RO permeate, and the product water, which is the UV effluent. So at these 4 locations, we sample for NDMA and for the 4 THMs. In the feed water, we also measure bromide because, as I said before, bromide is involved in the formation of bromamines and in the brominated THMs. So it's important to know what's the concentration of bromide coming into the treatment. And you can see too that in the RO feed, permeate, and the UV effluent, we measure DEHP, which is di-2-ethyl hexylphthalate. And this is not a disinfection byproduct, and it's not related to whether we use inline or preformed chloramines. It is regulated under CTR, and it's a chemical that's used in the plastic industry to make plastics more flexible. And there was an interest in this project to gather more data about this compound. So this study presented a good opportunity to do it. So that's why we added it to the test plan. This is how the preformed chloramine system, this is a schematic of the system, right? So starting from the left, we have the feed water coming in, and it's treated by MF and RO. And then after reverse osmosis, we take a side stream of the RO permeate and bring it back to the front of the MF treatment. And in this side stream, we preform the chloramines. So we do that by adding sodium hydroxide, and that is to increase the pH because the RO permeate has a pH of around 5, and we want the pH to be around 7 or 8 to form monochloramine. And then we add prechlorine in the form of sodium hypochlorite and ammonia as ammonium sulfate, and we preform the chloramines in the side stream. And one interesting point about this system is that we are forming the chloramines as a concentrated solution. And this means that this side stream is very small compared to the main process. So we are not using a lot of RO permeate, which is high quality water. So we inject the chloramines in the feed water to achieve our target residual that was 3 milligrams per liter. The dosing is based on the incoming flow that we measure here with the analyzer, the flow meter A, and also on the total chlorine that we measure after injection. For that, we have analyzer B, which is a total chlorine analyzer. And we also measure with this analyzer with the letter C, a free chlorine, because as I said before, we don't want to send any free chlorine to the membranes because that could damage them. This is how the system looks in real life. So as I said before, it has a low capital investment. It uses chemicals that are already at the site because they are used in other processes. Doesn't require any specialized equipment or treatment. It's just dosing pumps and static mixers. So if we start here at the bottom picture from the left, this is the RO permeate tank, and this gray pipe here is where the RO permeate goes to the UV treatment. So we take a side stream of the RO permeate and bring it to the sodium hydroxide dosing. And there's a close-up here at the top, right? So here we dose sodium hydroxide, then chlorine, and then ammonia. And then if you look down here on the bottom right, we have the injection of the preformed chloramines into the feed water. Okay, so now moving on to the results, I want to show you first the performance in terms of achieving our target dose, and that worked really well. So I said before, we were targeting a residual of 3 milligrams per liter after chloramine injection, and we measured that with our total chlorine analyzer, and those are the blue circles in the figure. So you can see we were always around 3 milligrams per liter. Then as the process continues, we lose some of that residual, which is normal, and that those are the green triangles. And also we measure free chlorine, which is the red squares, and you can see we didn't send any to the membranes, which is good. Another important part is that you want to make sure is that the pH in this side stream where you preform the chloramines is 7 or higher, maybe 8. So we monitor that. We were able to be always around 8, and that the objective of that is to make sure that we are forming monochloramine instead of dichloramine. So we took a sample of the concentrated chloramines and run a UV scan and confirmed that we indeed were forming only monochloramine. We had one peak corresponding to monochloramine. So now moving on to the more interesting part, which is the water quality results. This is the bromide concentration in the feed water. So we measure bromide before injecting the chloramines, and we want to know what's the concentration of bromide because it's involved in the formation of DDPs. So it was between 190 and 300 micrograms per liter, which is not considered a high concentration when you compare, for example, with seawater or with water that is affected by seawater intrusion. And we know that reverse osmosis provides very good rejection of bromide, so it's going to be very low in the RO permeate comparable to other US water sources. Okay, so these are the results for the THMs, and this was very encouraging. You can see here in this table on the left, we have the 4 THMs that we monitored. So that's BDCM, DBCM, bromoform, and chloroform. And here are the results for different points of the treatment. So we measure them in the feed water before injecting the chloramines, and you can see here they are all below 0.5 micrograms per liter. So we didn't detect them. And I don't know if I mentioned this before, but we monitor over 12 months, monitoring every week and sometimes twice a week. So we have a pretty complete data set. So then we inject the preformed chloramines. And at this point here, when we did the study in 2015 and 2016, we were doing inline chloramination, and this is where we saw that increase in the THMs. But now we measure here after injection in the RO feed, and BDCM, DBCM, and bromoform are still below 0.5 micrograms per liter. We did have some formation of chloroform, but it's looking much better than what we saw before. In the RO permeate then, both were on average, I mean, not both, the 4 of them were on average not detected. And then in the UV AOP effluent, all of them were consistently below 0.5 micrograms per liter. So this was very encouraging. This is telling us that adding the chlorine and ammonia in this way is helping us prevent or minimize the formation of DDPs, and we are achieving a product water that's CTR compliant. So we also monitor NDMA. As I mentioned before, NDMA can be formed when chloramines react with nitrogenous organics in the feed water. So it's a disinfection byproduct, but it's also a product of some industrial processes. So we could have it in the source water, and that was indeed what we saw here. So the blue solid dots are the NDMA concentration in the feed water, and you can see that we detected it at varying concentrations. Then we add the preformed chloramines, and we measure again here in the MF, in the RO feed with the red squares, and concentrations seem to increase slightly, indicating that maybe we formed some NDMA. We measure again in the RO permeate, and that's the green triangles. and the concentration decreased. So we are removing it through RO, but it's partial removal, which is consistent with what we've seen before. We know that the main mechanism of removal of NDMA is through photolysis in the UV treatment. And that's exactly what we saw here. We don't have symbols for the UV effluent because all of them were below detection. So we were efficiently removing NDMA in this treatment. So that's good news too. One thing that we looked at was the potential for NDMA reformation. And that's because some studies have reported that during UV treatment, when we have all these compounds being broken down, some of them could become NDMA precursors. And then in the transport to the reservoir, if there's still chloramine in there, we could have NDMA reformation. So we wanted to investigate this, and for that we collected samples of the UV AOP effluent and tried to simulate by allowing the time that the water would be transported to the reservoir, and then measure again. And we did the same for THNs, and both were still below detection. So we didn't have any indication that reformation was happening. So that's also good news. Excuse me. Okay, so this is the last of the results, and that's for DEHP. And as I mentioned before, this is regulated by CTR2, and we wanted to gather more data. We detected it sporadically in the RO feed and permeate, but it was consistently not detected in the UV AOP effluent. Our method reporting limit was 0.6, so less than 0.6 micrograms per liter, and that's well below the 1.8 micrograms per liter, that's the CTR limit. So those results look good too. So to conclude, we demonstrated with this study that preforming the chloramines in RO permeate helps maintain DVP levels that are below the CTR thresholds. BDCM and DVCM, which were the most concerning THMs, were always below detection in the UV AOP effluent. NDMA was below detection too. We did see some formation, but it was partially removed in RO treatment and then very well removed during UV treatment. So with this study, we demonstrated that preformed chloramines are a cost-effective way of achieving CTR compliance for DVPs, and we hope that this will make implementing preformed chloramines for surface water augmentation more attainable in California. So that was my last slide. I just want to finish by thanking you again for coming to this presentation, and thanking all the parties involved and funding agencies, and that's Padre, the San Diego County Water Authority, MWD through the FSA program, and the Bureau of Reclamation. So that's all I have. I'll pass it to Warren now.
Great, thank you. That was a terrific presentation, Luciana and Saval. We do have time for a couple of questions, and we actually have 2 questions here. The first one is from Joe and Clona. I hope I said your name right. And that question is, what is the target residual of preformed chloramines as it enters the membrane filtration?
Right, so we're targeting about 3 milligrams per liter for the MF system, and we know that we're going to lose some of that residual in the RO feed. We had more around 2.5, and we found that worked very well for controlling biofouling.
Great, thank you. Then the next question is from Roy Wolf. Always with the challenging questions, Roy. What is the chlorine to nitrogen weight ratio for chloramines? In other words, with a 3 milligram per liter of chloramines, what is the concentration of ammonia? And is there any excess ammonia that you're detecting?
Yeah, that's a very good point. And we did take that into account because, as I was saying before, we don't want to damage the membranes. That means we don't want to send any free chlorine. And to do that, we were dosing ammonia in excess to make sure that we always had a residual. We didn't measure it, but we were targeting a residual of around 0.2 or 0.3 milligrams per liter. And we controlled that by dosing the chlorine to nitrogen at a ratio of 3 to 1. So that ensured that we always had that excess free ammonia that ensures that we will not have any free chlorine and thus damage the membranes.
Fantastic, great. I'm going to invoke my moderator privileges and ask you a question based on a story that you told me a little while ago about melted pipes from a prior pilot test of this. I think this is important information for people to hear about. So could you tell that story for the group?
Sure. Yeah, I can tell you like what that's about, and it has to do too with a question that you had before about what lessons we learned. And we know lessons learned from studies and from other projects, and we try to implement all of that in this study to make it run really smoothly. So one of the things that have been observed was the issue of melting or damaged pipes, and that's because when you mix chlorine and ammonia, that reaction is exothermic, so it produces heat, and that could damage your equipment. So you want to make sure that you're never mixing those two without any water, like the carrier water or the RO permeate, to provide dilution and cooling. So we were aware of that, so we implemented controls to make sure that the chemicals were only injected in the side stream if there was a flow of RO permeate, and also if there was water coming into the system. And also we use CPVC for the preformed chloramine system instead of using like the regular or conventional PVC, because CPVC is heat tolerant. So it's a better material for this system.
Okay, I think we have time for one more question. Any questions from the participants? I am seeing none. Any other lessons learned you want to share from Saval or Luciana from your experience with this pilot test?
Well, in terms of like I was saying before, things that we knew from other projects that we wanted to make sure we considered in this study was, for example, the order of addition of chlorine and ammonia. That plays an important role in the water quality that you obtain. And so we, from studies, we know that if you add ammonia first and then chlorine, then adding chlorine second makes what happens is that you could have like localized regions with very high chlorine concentrations, and that could lead to the formation of dichloramine, which is something that we don't want, because we know that dichloramine reacts faster with the constituents in the source water to form NDMA. So to avoid that, we added chlorine first and then ammonia, and that helps you control for dichloramine formation and also for NDMA formation.
Fantastic. Thank you for answering that. And just one last question that I'm curious about is, can you go over the next steps? When are we going to get water discharge, drinking water discharged into the reservoir and start, getting product water from this project?
Yes, I can take that. So yeah, we are in the middle of design. We're moving towards 60% design. So our goal is to finish up with startup and commissioning by spring 2025, and really after that being fully operational. So we are driving towards that goal still, and we are implementing this. So this technology or this application in our project. So it's in our design drawings right now includes this. And I wanted to mention something that Luciana at the beginning showed 3 options available. And this is a new space, right? So this is not necessarily, the CTR is not a concern for groundwater recharge projects, I believe. I don't want to speak. I know more about surface water augmentation now. But it is new in our for this space, because we are discharging into local, we are discharging into inland bodies of water, and we are subject to CTR, which is way kind of lower than what other maybe recharge projects are dealing with. So this is when we realized, when we switched from working towards groundwater recharge to a surface water augmentation type, And this is a problem for other potential projects in the region. You'll be subject to these low limits. And those are the three options. Luciana showed maybe the mixing zone. That's actually, we explored that with regional board, and it's not favored for a surface water augmentation type projects because this is a lake, not an open water body. So they're not convinced that there will be a mixing zone. Eventually it will be all purified water in that reservoir. So they are, it's just not a very promising route. I don't think that they're gonna allow, and they say they require the project owner to do a lot of kind of studies proving that, which is you can only do after the project implementation. So it can be a holdup if you cannot convince. So I don't think that's a real practical option. So the real practical options are either investing in a air stripper or doing something like this with the chemical injection, changing how you're going to really inject the chemical, and doing a smart way of just preventing from the source and not really producing those chemicals.
Terrific. So
yeah, I hope this is valuable study. It will be available, right? It's
so we are at the end of our time. I would like to just go. We have one more question, and then I want to close it out. So another question from Joe, and if we could answer this really quickly, I think that'd be great. Do you have any issues about scaling or plugging of the injection quills based on their experience when injecting chlorine and ammonia to form chloramines? So did you have any plugging issues?
No, not that I know of. And I mean, the operators didn't mention it, so I would say no.
Okay, so I think that's all the questions we have for today. And Saval, thank you for that explanation. I totally agree with you that this is the way to do it. Terrific presentation, terrific pilot study. Congratulations on the success. I think not only did you prove out the technology, but you also laid out a model of how to do a successful pilot test. So really a terrific job, both of you. I want to thank our member agency partners, Jeremy, and also Nathan and Goldie. They were our member agency partners. They navigated the study through COVID, which wasn't an easy task. So terrific to work with, and we think we enjoyed working with you on this. I also want to recognize the Metropolitan FSA team, Hannah Ake, who tirelessly has been putting these webinars together and is also study lead for 4 studies. Don Bentley, who is the Metropolitan lead for this particular study, but also Matt Hacker, Arib Saeed, Stephanie Franco, Teresa Gonzalez, Ryan Roman, and Lauren Carrillo have also been helping us with the webinars. And without their outstanding work, this FSA's program and this particular webinar would not have been possible. Finally, I want to thank you all for taking the time out of your busy day to listen to yet another webinar. I know there's like a million of them. The next one in this series will be October 7th, also in San Diego County, and it's going to be on groundwater optimization. So I think this concludes the webinar. Please take care of yourselves, take care of each other. That's an order. And we'll see you next time. Thank you again.
Thank you. Bye.
Thank you.
all.
Bye.